we are investigating propagation of light inside an optical fiber. In the last lecture, we saw that optical fiber has a solid glass rod, what is called core, and a glass shell surrounding that rod, what is called cladding. We saw that if the light is incident on this optical fiber from the side, this light cannot be guided inside the optical fiber. So, only light can get inside the optical fiber if light is launched from the tip of the optical fiber. Then we saw that depending upon the launching angle, either the light ray can remain confined to the plane containing the axis of the optical fiber, which we call as a meridional ray, or a ray which does not lie in the plane containing the axis of the optical fiber. This ray spirals around the axis, and these rays were called as skew rays. Then we said the light can have sustained propagation inside the core of the optical fiber through multiple total internal reflections on the core cladding boundary. Then we also saw something more in depth about the total internal reflection, and all this we were doing by the ray model, which is the simplest possible model for light. So, today let us see little more insight into the propagation of light, still using the ray model. So, yesterday we had seen for total internal reflection, in the medium where light is total internally reflected, you have the superposition of these phase fronts, which give you the constructive or destructive interference, and because of that you have a standing wave kind of pattern in this region. This region is same as the core region of the optical fiber, and then we have an exponentially decaying field in the cladding, and this field theoretically at least extends up to infinity. Then we have said that for total internal reflection, three things are to be noted. One is the standing wave type of field inside the core, decaying field inside the cladding, and when the phase undergoes at the total internal reflection, there is a sudden phase change at the boundary. So, you have these three things happening when the total internal reflection takes place. Then we had taken this simple figure here, saying that if we consider the two rays which are parallel, and these are the phase fronts, this phase front is common to these two rays. Similarly, this phase front is common to this ray and the total internally reflected ray twice at this interface and at this interface. And then we said if we have to have a sustained propagation, then there has to be this phase condition satisfied that the light interferes constructively, so that you have a propagation of light inside the core. And then by using simple geometry, we got the phase condition that if this condition is satisfied, then only the light can get launched inside the optical fiber. If this condition is not satisfied, then the light is not launched inside the optical fiber. So, we made a very important observation that even within the cone of numerical aperture, if a light ray is launched at an angle which does not satisfy this phase condition, then that ray cannot propagate inside the optical fiber. So, we have said that if we consider optical fiber like this, this is the cone which is the numerical aperture cone. Earlier, when the phase condition was not needed, any ray lying within this cone would have had total internal reflection and would have propagated through this core. However, now what we are saying is that only at certain angle the ray can get inside the structure, and any other angle the ray cannot propagate inside the structure. Now, as I mentioned earlier, whenever we are saying a particular angle, we are essentially talking about all rays which make the same angle with the axis of the optical fiber. So, when I say this ray, essentially this ray corresponds to a ring which is making an angle this theta with respect to the axis. So, one thing to note here now is that if I consider a ray which is launched along the axis of the optical fiber, this ray does not require any condition to be satisfied, because there is no total internal reflection for this ray. This ray essentially does not go to the boundaries. So, one can say that if a ray is launched in this direction without any spatial condition, this ray will always propagate inside this optical fiber. So, that means a ray corresponding to theta equal to 0 will always propagate inside the optical fiber. However, the next ray which can be launched inside the optical fiber has to satisfy this condition now. So, one can say that the ray which goes along the axis of the optical fiber, since there is no total internal reflection, does not go to the boundary, delta is equal to 0. You can take m equal to 0, that is the first ray which can propagate. So, you get theta equal to 0, that is the ray which is going to propagate. That is this ray which is along the axis. If I now go to the second value of m, which is m equal to 1, then now I require certain value of n1d for a given lambda, so that this condition is satisfied. What that means is now that the next angle which can propagate inside the structure could be this angle. And as I mentioned, this angle essentially means all the rays which are making the same angle with respect to axis. So, essentially it is this ring which is going to propagate inside this optical fiber. So, one ray is the one which is going straight like this. Second is the ensemble of rays which are making this angle. Third could be this one, and that is all. So, what we find now is that there are discrete ensemble of rays which can be launched inside the optical fiber. And when we take the ensemble of these rays, the collection of this ensemble or the rays, that gives you interference pattern inside the core, and as a result you have a very definite intensity patterns formed inside the core of the optical fiber. So, for every value of theta, you have a unique intensity pattern created inside the optical fiber. And this unique intensity pattern essentially is what is called the mode of the optical fiber. And as the angle increases higher and higher, we say that the order of the mode increases. So, the mode which is created inside the optical fiber corresponding to the ray which is launched along the axis, that mode we call as the lowest order mode. Then there will be next mode, then there will be next mode, and beyond the numerical aperture the ray cannot be launched inside this. So, you have a finite number of modes which can propagate inside the optical fiber. So, two things should be noted at this point. One is you are having discrete intensity patterns which can survive inside the optical fiber. Any arbitrary distribution cannot survive inside the optical fiber. And secondly, these patterns are discrete and they are finite in number, because any ray which is having an angle greater than the numerical aperture angle, that cannot be launched. So, if you can literally count the angle at which the rays can be launched inside the optical fiber. So, now we see that even if you have a numerical aperture cone which is as large as this, the light launching efficiency is further reduced, because every ray which is lying within this cone cannot go inside the optical fiber. So, fiber chooses only light coming at those angles, and any other light essentially is rejected. So, the efficiency of launching inside the optical fiber is further restricted. So, if I now consider this variation of the intensity inside the optical fiber because of the constructive or destructive interferences, we may get various kind of patterns. You may have maximum at the center, and then the field may die down slowly toward the end of the edge of the optical fiber, or is possible it may be maximum at the center, goes to 0, again rises towards the walls of the optical fiber, and so on. One more thing one can note at this point is that, let us say when the ray is launched like this, if a ray goes along the axis of the optical fiber, and now slowly try to put the wave phenomena behind this. So, let us say this ray is a transverse electromagnetic wave now. So, you have a electric field, you have a magnetic field. So, if I consider this ray, then the electric and magnetic field are perpendicular to each other, and they are perpendicular to direction of propagation of this ray. So, let us say the electric field lies in the plane of the paper. So, for this ray it will always lie in the plane of the paper, and since the net propagation is along the axis of the fiber, you have the electric field which will be always perpendicular to this. If I consider a ray which goes at an angle like that, and if I consider now the electric field, let us say, is coming perpendicular to the plane of the paper, then this is the direction of the electric field. Then E cross H should give me the direction of the power flow. So, you should have, this is the magnetic field. So, the electric field is perpendicular to direction of propagation for all the rays which are going to be lying on this surface, whereas the magnetic field has a component which is in this direction and which is in this direction. So, in this situation, we find that the electric field component is always perpendicular to the net propagation of light inside the optical fiber. And this propagation, therefore, we call as a transverse electric propagation, because the electric field always remains transverse to the direction of net propagation of light inside the optical fiber. So, I have a mode what is called transverse electric mode, which we denote by TE, and then we put some index for this mode, essentially telling us how many maxima minima the interference pattern would create inside the core of the optical fiber. Instead of electric field perpendicular to this, if the magnetic field was like that, then the electric field will lie in the plane of the paper, and then you will have the electric field components in the direction of propagation, and the magnetic field will remain always perpendicular to the direction of propagation. So, as we got the transverse electric mode, we will also get the transverse magnetic mode, and again depending upon the variation of the intensity, you will have some index defining the transverse magnetic mode. So, you have a mode which will be transverse magnetic mode, or we denote by TM mode. So, as we now see that if you consider the rays which are meridional rays, because these rays which you have drawn here are meridional, they are lying in the plane which is containing the axis of the optical fiber. The superposition of all these rays which are going at a certain angle would create a electric and magnetic field patterns which could be either transverse electric in nature or which could be transverse magnetic in nature. Compare this now with the skew rays which are going at a certain angle with respect to this meridional plane. So, if I consider, let us say, optical fiber like this, and the ray goes at an angle which is not in this plane, but it is something like this. If that happens, as we have seen, this ray essentially spirals around the axis of the optical fiber, and as a result you can show that in no circumstance you will have a configuration which will have purely transverse electric in nature or which will be purely transverse magnetic in nature. So, if we consider the skew rays, they would have electric and magnetic field, both components, in the direction of net propagation of light. This mode then is neither transverse electric in nature or nor transverse magnetic in nature. That is the reason if I consider the skew rays, they essentially give rise to a phenomena what are called the hybrid modes. Those of you who have done waveguides earlier, they know that in a metallic waveguide, you have the electric and magnetic field distributions which are either transverse electric or transverse magnetic. There is nothing like a hybrid mode which exists in the metallic waveguide. However, when we come to optical fiber, which essentially is a dielectric waveguide, there in addition to transverse electric and transverse magnetic modes, we also have another set of modes, what are called the hybrid modes. And later on we will see hybrid mode is the lowest order mode which essentially propagates inside the optical fiber. So, in fact, the ray which goes along the axis of the optical fiber, when we do the rigorous analysis, we will find that mode is neither transverse electric nor transverse magnetic, nor transverse electromagnetic, but it is the lowest hybrid mode which essentially propagates and which corresponds to the ray which goes along the axis of the optical fiber. So, now we find that just from the ray model and just putting the phase fronts behind these rays, we get a reasonably in-depth understanding of propagation of light inside the optical fiber, and that is we have discrete intensity patterns created because of interference of the phase fronts, and these intensity patterns could be transverse electric in nature, could be transverse magnetic in nature, or could be hybrid in nature. So, now if I look at now the intensity patterns which are created, we may have a situation something like this. If the angle at which the ray is launched is reasonably low with respect to the axis, then you will get maximum at the center and slowly the field will decrease because of the reduction in the constructive interference, and by the time you reach to this core cladding boundary, the field has reached to this value, and beyond this the field exponentially dies down in the cladding. If I have the angle further increase, then there is a possibility now that you will have a maximum at the center, field goes to 0, again increases with reverse direction in the field, and then reaches to the core cladding boundary and then exponentially dies down. So, how many zeros are crossed in the transverse direction? That essentially defines what is called the index for the mode. So, if I have a field distribution which will look like that, no zero is crossed, so we can call this distribution as transverse electric. 1 0 is there, so we can call this distribution as T1, this we call T0, and here the 2 zeros are there, so we can call this distribution as T2. So, like that, as the angle of launching increases, you see more and more zeros in the intensity pattern, and that essentially is reflected into this index which is put along with TE or TM. So, although the figure shown here is for transverse electric case, the arguments are also true for transverse magnetic. Now, coming back to again the launching of the rays inside the core of the optical fiber, the thing which we noted now is that there are only discrete rays which can go inside the optical fiber. One ray which is along the axis is always guaranteed because it does not require any phase condition to be satisfied. But the next ray which can go will depend upon whole lot of parameters. So, as we saw, it depends upon the quantities which are the fiber parameters, like the diameter of the fiber D, the wavelength of operation, the refractive index of the core material. So, these are the parameters which essentially will tell us at what angle this next ray can be launched inside the optical fiber corresponding to m equal to 1. So, now one can ask a very simple question. Is it possible that only the ray which goes along the axis of the optical fiber is launched, but the next angle which satisfies the phase condition is more than the numerical aperture cone? Why do I ask this question? Because we have seen that when a pulse of light is launched inside the optical fiber, and if large number of rays can propagate inside the optical fiber, the pulse energy get divided into different rays. Different rays effectively travel with different velocity because they go by different paths, and because of that there is pulse broadening. So, as we saw earlier that the pulse broadening is related to the number of rays which can go inside the optical fiber. So, if I could reduce the number of rays inside the optical fiber, obviously the pulse broadening also is going to be reduced. That is the reason we are asking this question, that suppose I make a condition so that only one ray which goes along the axis of the optical fiber is launched, but the next ray which satisfies the phase condition cannot be launched because that angle is more than the numerical aperture angle. Then there is no question of now pulse broadening, because the entire pulse energy is going to go only by the ray which is moving along the axis of the optical fiber. So, we see that if I reduce this quantity d, or if I make this quantity n1 small enough, but n1 we can't change too much because we have already identified the material glass. So, only this quantity d upon lambda, or for a given value of lambda, the diameter of the fiber, if I reduce the d to a substantially low value, then for any angle you cannot satisfy the phase condition even for the next value of m, which is equal to 1. Or in other words, what we are saying is, if I make the optical fiber core thin enough such that only this ray which goes along the axis can be launched, but even the second ray which satisfies the phase condition cannot be launched because this angle is greater than the numerical aperture angle. By doing this, essentially then one can avoid the pulse broadening on the optical fiber. This phenomena of pulse broadening, later on we will see, is what is called dispersion on optical fiber. So, essentially by reducing the number of rays or creating a situation where only one ray can go along the axis of the optical fiber, the dispersion on the optical fiber can be eliminated. And that is a very attractive thing, because we know that the dispersion or the pulse broadening has direct implication on the data rate. So, if I could create a situation where only one ray goes, then I can transmit a very high data rate on the optical fiber. So, now I have a situation where large number of rays go and energy propagates on the optical fiber, or second situation is only one ray goes along the axis and there is no dispersion on the optical fiber. Since we have seen that each ensemble of rays launched at a certain angle creates a definite intensity pattern which we call as modes, when many angles are possible inside the optical fiber, we call that fiber as the multi-mode fiber. And by the same token, when only one ray goes along the axis of the optical fiber, we call that fiber as the single mode optical fiber. So, one thing is clear, if I have the diameter of the fiber reasonably large compared to the wavelength, then I have a large number of rays going inside the optical fiber and I have a multi-mode optical fiber. If I reduce the diameter of the core to a reasonably low value, then I may get only one ray launched inside the fiber, or one mode will propagate inside the optical fiber, and that fiber we call as a single mode optical fiber. So, then from dispersion point of view, the multi-mode optical fiber is very bad fiber because it has a very large pulse broadening, and single mode optical fiber is the best optical fiber because it does not have any dispersion. only one ray goes inside the optical fiber. However, one would notice that if the diameter of the fiber is reduced to a substantially small value, then and numerical aperture cone also will reduce in this process. Only one ray can be launched along the axis. So, the launching efficiency of this fiber is extremely small. So, a launching light inside a multimode optical fiber is easy because it has a large diameter, it has a large numerical aperture cone. So, you can launch a light very easily. If I consider a fiber which is single mode optical fiber, then the light can be launched only along the axis. So, you require a source which can give you a highly beamed light, highly collimated light, then and then only light can be launched efficiently inside the single mode optical fiber. So, single mode optical fiber gives you advantage of dispersion, but at the expense of the launching efficiency of light. So, you require very special kind of sources like lasers, so that light can be launched inside single mode optical fiber, but any other source like LEDs are quite suitable for multimode optical fiber. If you take a source like LED which does not give you a very collimated beam, and if you put a single mode optical fiber in front of LED, hardly any light will get launched inside the single mode optical fiber. So, now just to give you numbers, a typical multimode optical fiber would have a diameter. So, you have multimode fiber, it has typical diameter of the order of about 50 to 100 micrometer. And if I consider a single mode optical fiber, then we have a diameter typically in the range of 6 to 8 micrometer. So, you can see that when we have a single mode optical fiber, the diameter is really very, very small, and that is the reason the light has to be very precisely focused on the core, so that it can get efficiently guided inside this fiber. Though the diameter of core is different for the single mode or multimode optical fiber, the diameter of the cladding is always standardized to 125 micron. And the reason for this is very simple, that whether you have a single mode fiber or you have a multimode fiber, ultimately you would like to put a connector on this fiber. So, fiber has to go inside the connector. So, the inner diameter of the connector should decide what should be the outer diameter of the fiber which goes inside this connector. So, irrespective of what is the diameter of the core, the cladding diameter is decided by the inner diameter of the connector which you are going to put on the fiber. And that is the reason the cladding diameter has always been standardized to 125 micrometer. 125 micrometer. So, irrespective of whether I am using a single mode optical fiber or I am using a multimode optical fiber, the cladding diameter is always will be 125 micrometer. So, now we have introduced nomenclature for fibers. The multimode optical fiber, which carries large number of modes, has a diameter of 50 to 100 micrometer, has a very large dispersion because large number of rays are going to propagate in this. And then we have a single mode optical fiber which has a diameter of 6 to 8 micrometers, has no dispersion because only one ray propagates on this, and it has a very low launching efficiency, but has a very good dispersion performance, and the cladding diameter is standardized to 125 microns. So, when we start using the single mode optical fiber, we get the dispersion advantage, but at the same time we have a very difficulty in launching the light inside the fiber because the size of the fiber has become very small. One can then ask a question can we do something so that I still have the size of the fiber still reasonably large, but the dispersion on the fiber is reduced? So, to answer this question, again go back to the basic ray model inside the core and ask, if I have to reduce the dispersion, what is to be done to the ray propagation? So, let us say this is the fiber core. A ray which is launched along the axis will go like that. Now, we saw if the ray was launched at an angle which goes like this, it travels a larger distance, and because of that the effective distance travelled along the axis of the fiber is less as the angle becomes larger and larger. Since the velocity of this ray and this ray is same, and this ray travels a longer distance, so there is a time difference created between this ray and this ray. This is what essentially gave rise to the dispersion phenomena or pulse broadening phenomena. So, suppose we can create a situation where the ray which travels a longer distance travel with a faster speed. Suppose it is possible. Then the ray which is going by this path will travel a longer distance, but will have a speed which is higher than the ray which is going by this path. So, now there is a compensation in time. So, you will not have a separation of the rays as they used to be when the velocity of this ray and this ray was same. So, if we can create a structure where the ray which travels the farthest distance travels with the fastest velocity, and the ray which travels the shortest distance travels with the lowest velocity, then the dispersion is reduced on the optical fiber because there is a time compensation which has taken place. So, essentially we are looking for a mechanism by which the velocity of light can be manipulated. And as we have seen earlier, this is very simple because the velocity of light depends upon the refractive index of the medium. So, if you can change the refractive index of the medium inside the core, then the velocity of light will change. And if I want the ray which are going to the higher angles, if they have to travel faster, essentially the refractive index must reduce for a region which is somewhere here, and the refractive index should be highest here. So, if I can create what is called the grading of the refractive index profile, then the ray which goes along the axis will be travelling with the slowest velocity. The ray which goes at an angle, as it goes at higher and higher layers of the optical fiber, they will travel faster and faster, and because of that the dispersion will be reduced. So, instead of having a refractive index profile which was constant in core and constant in cladding, N1 here and N2 here, suppose I create a refractive index profile which looks something like that. So, this value at the center is N1, this is the cladding where refractive index is N2, but the refractive index gradually varies from center of the fiber to the core cladding boundary. As a result, what will happen? This ray will travel with a velocity which is c divided by N1. The ray which is going at a slightly higher angle, which will go like this, and then now every ray will not go up to this point. The ray will go like that, which has a certain angle, and will come and join here. The ray which goes higher will travel faster and faster, so will go like this, come like this. The ray further goes, go like this and like this. So, essentially now the ray propagation is going to be like a projectile inside this fiber. So, the rays would start from here, they go like this, but since this ray will start travelling faster and faster, by the time this ray has travelled from here to here, this ray would have again come and join here. So, it will start like this, join like this, like this, like this. So, since we have now graded the refractive index profile of this optical fiber, we call this kind of fiber as the graded index optical fiber. So, inside a graded index optical fiber, we have a large number of rays propagating. The diameter of this fiber is same as the diameter of the multimode fiber, but its dispersion is much lesser compared to the multimode optical fiber. Of course, you can never have a perfect matching of the time for different rays. This will give you a performance not as good as the single mode optical fiber performance, but it can give you a performance much better than the multimode fiber performance. So, one can show with rigorous analysis that if you take this profile, the refractive index profile, which is parabolic in nature, then you get the best possible time compensation and you get the least pulse broadening on this optical fiber, graded index optical fiber. So, now we see in practice there are three types of optical fibers. The multimode optical fiber, which has refractive index constant in the core and constant in the cladding, and that refractive index profile is like a step function. So, if I consider a simple multimode fiber, the refractive index profile will look like that, where this is N1, this is N2. So, this refractive index profile we call as the step profile. So, we can call this fiber as the step index multimode fiber. So, we can have here step index, or we can have a graded index fiber, multimode fiber, or we can have a single mode fiber if you can create a diameter typically of the order of 6 to 8 microns. So, if I arrange them in the order of performance for dispersion, the multimode step index fiber is the worst fiber because that has the highest dispersion. Much better than that is the graded index optical fiber, which is multimode again, but for the parabolic variation of refractive index, it gives you dispersion 100 times better compared to the multimode optical fiber, and the best will be the single mode optical fiber, which is about 10 times better compared to the graded index optical fiber. So, now let me just summarize what we said. We said we have three types of optical fibers in practice now. The best fiber is the single mode optical fiber, where the core is very thin here, the diameter is about 8 microns. This is the refractive index profile, and only one ray goes inside this optical fiber, and this is the best optical fiber because for this the dispersion is very low. This is the fiber which is multimode optical fiber, where this core is 50 to 100 microns. The refractive index variation is a step, and it has the worst possible dispersion performance. In between these two is the graded index optical fiber, where the refractive index profile is close to parabolic, and this gives you a dispersion which is about 100 times better than this and 10 times worse than this. So, if you do not want to sacrifice too much on the launching efficiency, then multimode graded index fiber is the better option than going for the single mode. So, utility wise, then one can say that if my data rate is not very large, or if my distance is not very large, then a multimode graded index optical fiber is a good choice, because it does not require special kind of sources. Even LED kind of sources would be good enough to launch light inside these fibers. Whereas, when we go to very long distance high speed communication, then even graded index optical fiber dispersion performance is not adequate. So, we will go to the single mode optical fiber. So, in fact, the multimode optical fiber with step index is only for the academic interest, and maybe this kind of fiber will be used in the laboratories. But if you go to the small networks like local area networks, at least you will use the fiber which is the graded index optical fiber with a refractive index profile very close to parabolic. And when we go to the long distance high speed communication, the most of the time the fiber will be the single mode optical fiber. So, this is now the basic understanding which we have developed from the simple model, what is called the ray model. One can ask a question, can we just stop here and need not go for the wave model? The answer is no, because the ray model gives you some insight into the propagation of light inside the optical fiber. Still, it does not describe the complete propagation of light, and the reason is very simple. Suppose we ask a question that the ray which goes along the axis of the optical fiber does the propagation characteristic depend upon the wavelength? If I just consider the ray model, the answer will come no, because I am considering a ray irrespective of what is the frequency or what is the wavelength of this wave. This is the ray which will go along the axis of the optical fiber. So, propagation of light does not depend upon the wavelength of operation. However, that is not correct. When we talk about a bound medium like this, then the propagation characteristic depend upon the wavelength of light. So, the ray model gives us some understanding of propagation of light inside the optical fiber, but if you wanted to have a quantitative understanding of propagation of light, or if you want to find out how much pulse broadening actually is going to take place, or would there be pulse broadening if there is only one ray which goes on the optical fiber, but if the source had a finite bandwidth, these questions cannot be answered by the ray model. And that is the reason we essentially go and investigate in detail what is called the wave model of propagation of light inside the optical fiber. So, here now idea is that having understood now the propagation of light inside the optical fiber in the ray model, make use of this physical understanding of propagation of light, and then try to go to the wave model, put this physical understanding into the analytical approach, and then try to get the quantitative answers to the physical understanding which you have developed here. So, before we get into the propagation of light by using the comprehensive wave model, let us first ask why analyze a wave model, what are essentially we are looking for. So, first thing is we are asking if the structure is given to you, which is like an optical fiber, and if the light is not propagating now in the form of rays, suppose the light is launched inside this, some kind of electric and magnetic field patterns will be produced inside the core. These patterns are going to propagate inside this. So, suppose we had now a source which has a finite bandwidth, then the pattern of electric and magnetic fields would be created at all possible frequencies which are within that band. So, the question one can ask is, if I change the frequency, how much the velocity is going to change of this modal pattern or the field pattern which are created inside the optical fiber. So, the quantity essentially we are looking for is here is the behavior of velocity of the electric and magnetic field patterns as a function of wavelength inside an optical fiber. So, the basic relationship which we have for the propagation of electromagnetic wave, light also is electromagnetic wave, is the relationship between the phase constant which we defined earlier as beta and the frequency omega. So, let us say if I had a certain field distribution here which travels with a phase constant beta. And this phase constant now is a function of frequency. So, we have a relation which is the beta omega relation. This relation is also called as the dispersion relation. So, by using the electromagnetic theory and the wave propagation in this bound structure which is the optical fiber, we find the relationship between beta and omega, and once you get beta and omega, then we can find the velocity of the field inside the core. And then as we know, for a wave there are two velocities, one is called the phase velocity, other one is called the group velocity. So, we have Vp which is phase velocity, which is omega by beta, and we have Vg which is group velocity, which is d omega by d beta. So, inside the optical fiber, since we are interested in sending light in the form of pulses, we are interested in this velocity, what is called the group velocity. So, in the next lecture when we meet, essentially starting with the basic wave equation, we satisfy the boundary condition on the core cladding. From there, we try to establish a relationship between the phase constant and the frequency omega. From there, then we get a velocity which is group velocity for a pulse from d omega by d beta. And once we get a group velocity, then we can ask a question that if light pulse was launched inside the optical fiber, how different frequency components will travel, and because of the variation in the group velocity, how the pulse is going to get deformed inside the optical fiber. So, this analysis of wave model is essential in finding out quantitatively the variation in the velocity of a pulse inside the optical fiber, which gives you information about the distortion of the signal on the optical fiber. So, when we meet in the next lecture, we start with the basic Maxwell's equations, treat the problem as a simple boundary value problem, and then find the propagation characteristics of a mode inside the optical fiber.